Hello everyone, this is Aryan.
Kashish here.
Wajahat here.
This is Prashidi.
And we seem to have a problem. Consider two line charge densities superimposed on each other. The negative charge moves to the right, whereas the positive one moves to the left. And Wajahat is a really positive person. Hey Wajahat, मैं और कशिश यहाँ पर है, यहाँ पर आ जा.
हाँ आ रहा हूँ.
अरे तू वहाँ क्यों जा रहा है अफ्रीका में?
Ah, this electric field.
It's not the electric field, it's the magnetic field. Now what may the reason be for their disagreement? Well, the Maxwell's equations are fully relativistic. That is, they are compatible with special relativity by nature. Thus, it should not be surprising that electric field and magnetic field are frame dependent. Now consider the following situation, which will help us understand how Wajahat and Prachiti are both correct in their respective frames. Consider our prior setup where the total current I is given by 2 lambda V. Consider the two cases that arise from this setup. In your first case, you are observing the setup from a ground frame which is stationary. We consider a positive test charge which we shall call Mr. Griffith, who is moving towards the right with some velocity u such that u is lesser than v. A white neutral ball has been added for better visualization of the trajectories. Here, the red balls are negatively charged and the blue balls are positively charged, and Mr. Griffith and the white ball are about to start moving. Notice that Mr. Griffith deflected away from the line charge densities.
So, how do we explain this? Here is a snapshot from the previous video where you can see the charge densities at a particular instant of time. Taken any cross section at any given time, you can see that the net charge is 0. Currently you can see there are 3 positive charges and 3 negative charges which cancel out, hence the net charge is 0. You can consider any particular cross section and still the net charge will be 0. As the net charge is 0, at any point near the charge densities, the electric field will be 0. Hence, there will be no electrical force acting on any charge kept near the densities. But there must be a force acting, and what is producing this force, we don't know yet. Before we look deeper into this, let's consider another situation.
Consider a frame where the observer is moving to the right with a constant velocity u. Observe that in the video, when the observer starts moving to the right with the velocity, you can see that there is a net contraction between the positive charges. This is because the net charge density is no longer 0 in this case, as there is difference between the relative velocities of the positive and negative charge densities. How do we explain this?
To now quantitatively discuss what we just saw in the video, let us consider a few derivations. So for that, you have your negative charges that were imposed on the positive charges. For now, let us consider that they are at rest. All these charges are at rest. The distance between them is so small that we can consider these discrete charges as a continuous line charge, having the line charge density, say, lambda naught. Now, consider a frame of reference. This is your stationary frame, and we are going to denote it with S. So this is our S frame. In this frame, now consider your positive charges moving towards the left with a velocity v, and your negative charges moving towards right with a velocity v. Both the velocities are same. Now consider one positively charged particle and one uncharged particle. The positively charged particle is Mr. Griffith, as we saw in the video. These both are moving with a velocity u towards the right, and we have a frame which is on the uncharged ball that is also moving with these charges with the same velocity of u. Let this frame be your S dash frame. Now, since the charges are moving, our charge density changes from lambda naught to lambda. Lambda here is given by gamma times lambda naught, where gamma is your Lorentz factor. This Lorentz factor is given by Now, since both the velocity of the positive line charge and the negative line charge is the same, the gamma factor is same for both. So the positive charges I have the new line charge density of lambda or lambda plus, which is the same as the line charge density for your negative charges or lambda minus. So your lambda plus is equal to lambda minus in this case, just because the velocities of both are the same. And this is the reason why we net charge density is 0. We have no electric field acting in this frame.
What the story is from Kashish's frame, that is the S frame. Let's take a look at what is happening in the S bar frame. I'll just quickly explain what this entire setup is about. The negative line charge density is moving to the right with velocity v. The positive one is moving to the left. And we are moving to the right with velocity u. We are basically sitting on the white neutral ball. And Mr. Griffith is also moving to the right with velocity u, and he is positively charged. So in the previous frame, we were observing from the ground frame, and that is why we saw that both of these velocities are equal. But now the frame is actually moving as well in the right direction with velocity u, and that is why the velocities which we perceive from this frame will be different for the positive charge as well as the negative charge. Let them be v plus and v minus. This I'll just point out once again that we are observing from the S bar frame. Now the change in densities is actually accounted by Einstein's velocity addition rule, which is given by v plus is equal to v plus u divided by 1 plus vu upon c square. And v minus will be given by v minus u divided by 1 minus vu upon c square. Because there is a difference in velocities, the Lorentz factor associated with these will also be different. Let that be denoted by gamma plus and gamma minus. The change in these two scenarios is going to be that the Lorentz factor is now going to be equal to 1 divided by square root of 1 minus v plus square divided by c square, and gamma minus is going to be 1 divided by square root of 1 minus v minus square upon c square.
So v plus is the velocity of the positive line charge density as seen from S prime frame. So this will be v plus, and v minus is the velocity of negative line charge density as seen from S prime. So this will be v minus. And now we have to calculate the Lorentz factor gamma. So we will just put the value of v plus this into this, and we will do some algebra, and we will get the gamma plus to be 1 upon under root 1 minus v square by c square, 1 plus uv upon c square divided by under root 1 minus u square by c square. Similarly, we can calculate the gamma negative, and that will be 1 upon under root 1 minus v square by c square, 1 minus uv upon c square whole divided by under root 1 minus u square by c square. So look at these two equations. These two equations, you can see this is constant, this is constant, and this is constant. So the only this is constant. The only difference in these two equations is given by this numerator, and you can see this numerator is greater than this. So easily we can infer gamma plus is greater than gamma minus. We can now calculate the densities using this Lorentz factor given by the formula lambda equals to gamma times lambda naught. We will just use this relation that gamma plus is greater than gamma minus. So lambda plus will be gamma plus times lambda naught, and gamma minus will be lambda minus will be gamma minus times lambda naught. As gamma plus is greater than gamma minus, lambda plus will be greater than lambda minus. So the densities here will now not be this constant. It will be the density of positive charges will be greater, and as compared to the density of negative charges. Okay, so this is what the situation will look like from S prime frame. And now if you take any particular cross section area, you can see that the net charge is now not 0. You will now see that the electric field will also be not 0. You can calculate the electric field. The electric field for a line charge, infinitely long line charge, is given by E is equals to okay, first we will just calculate the total lambda. That will be gamma plus gamma minus times lambda naught. We know the value of gamma plus, we know the value of gamma minus. We can do furthermore algebra, and we get the lambda total to be 2 lambda u v whole divided by c square under root 1 minus u square by c square. This is the total lambda, and also you can see in this equation the total lambda comes out to be positive, and you can relate with this situation that where the total charge density is positive, hence this value is also positive. Now we can calculate the electric field due to this charge density by a infinitely long wire, which is given as lambda total whole divided by 2 pi epsilon naught d. And d here is the distance from the line charge density of the positive charge or your point of consideration. This is d. You know the value of lambda naught, you know d, you can calculate the electric field, which is again coming out to be non-zero. Hence in this frame there is some electric field, whereas you can see in the frame of Kashish the electric field was 0 due to net charge density, which was 0. Here the net charge density is non-zero, hence the electric field is also non-zero. If there is electric field, we get an electric force, which is given by force is equals to QE, and Q is the charge on Griffith, or this positive charge. So I will write this force as S prime, because we are considering all this situation from the prime frame, S prime frame. So F prime will be given by Q times electric field, which is this lambda total whole divided by 2 pi epsilon naught d. You can further put in the value of lambda total, then we get F to be Q times lambda V U divided by pi epsilon naught C square S d under root 1 minus U square by C square. And you can see all the values are positive over here, hence F prime is non-zero. Hence there is some force, electric force in this frame, whereas in the case 1 there was no electric force.
So what we have until now is
There is definitely no force acting in S frame, which is electrical. And the second thing that we know is there is a force which is electrical, which is acting in S prime frame. We have been a little sneaky and we have also very coyly deluded you from discussing all the forces in S frame. So now let us move on to that discussion. We have a force as F prime in S prime frame, and we have no electric force in S frame, but it is a general fact that if there is a force acting in S prime frame, there has to be a force to account for the deflection that we saw in the video in S frame as well. How will we go on finding that force? So let us see that. Consider two frames as we have. This is say S frame and this is S prime frame. This F prime frame force is acting in this frame. Here, with respect to S, this S prime frame is moving towards right with velocity u, because remember, we were observing from the perspective of the white ball, which was moving towards the right with velocity u. We have this F prime force, which is electric in nature, therefore it is repulsive, because as we saw in the video also, this is perpendicular to this velocity. This is F prime. I want to find a way to have a force that accounts for the same effect in this frame also. How is that done? That is done by the force transformations. What we have until now been looking is the transformations of velocity, transformation of mass, but we have not yet studied the relativistic transformation of force. So there are, as we all know, force is basically the time derivative of momentum. In relative case, this momentum will just be relative. Now what is this relativistic momentum? It is given by this gamma factor, the Lorentz factor, this rest mass V by dt. Yes. So this is how we'll basically find out the relativistic force. Now there is again a mathematical trick to find the transformations. What we do is we resolve the forces into two directions. Now say this S prime frame is moving towards right. So if I have say some force in arbitrary direction, I will resolve it one along the velocity, one perpendicular to the velocity. So the transformation for both kinds of forces is different. If the force is say perpendicular to the velocity of the frame, then the transformation is so, F prime is given by gamma times F, where again F prime is in the relative frame and F is in the stationary frame. If the force to be transformed is along the direction of the velocity of the frame, F parallel, then the transformation is given by gamma cube F. So I won't go into the derivatives, you'll have to believe me on this one. In this case, clearly we can see the electric force, which was repulsive in nature, is perpendicular to the direction of velocity u, this perpendicular. So the transformation that will work is this one. We'll be using this case. We have the formula for F prime. F prime is given by this Lorentz factor times F, which is in stationary frame. What we want to calculate is this F. Simple rearrangement of terms will give us F prime upon gamma. So right now we have everything that we need right in front of our eyes. I want to calculate this F. I know this F dash, which is given over here. So let's go. F is equal to just pi epsilon naught c square d 1 minus u square upon c square. When so gamma is, as we know until now, 1 upon 1 minus u square upon c square. So 1 over gamma is basically this in multiplying numerator 1 minus u square upon c square. Right, have I got that correct? Yes. This and this gets cancelled out. Now here again, I want you guys to notice over here lambda times v. Initially when we had considered our setup, there were some positive charges moving towards left, I suppose, and negative charges moving towards right. I may have drawn the directions wrong, but it still suffices to say that these constitute a current. Essentially, positive charges moving towards the left is the same as negative charges moving towards the right. We consider conventionally the current to be in the direction of the positive charges. So if and each of them have a line charge density of lambda. So the total current flowing through this cross section, say I, can be given as 2 times lambda times v. V is because v is the velocity. This is the total current that we have. Here we have lambda times v. So I want to substitute this I. So simply we get lambda times v is I by 2. I am substituting this in this force again. So here I get F is equal to, instead of lambda v, I am plugging in I by 2, q I u by 2 here, and we still have pi epsilon naught c square d. Again, Maxwell equations, c square, what is the value of c square? It is 1 over epsilon naught mu naught, the constants. So now I am substituting the value of c square in this. I get finally F is equal to q pi upon 2 pi epsilon naught 1 over epsilon naught mu naught d. That's how you get q mu naught I upon 2 pi d. So look what we have here. You may recognize this as the equation for force, magnetic force due to a long current carrying wire. This is basically the magnetic force acting on a particle of charge q, which was the charge of Griffith, and it was moving at velocity u, and this is the magnetic field at that point. Please notice that we have never invoked magnetic field per se in the derivation. We have not even went for the Lorentz force, and yet what we get here is a purely electric force F prime, which was in S prime frame, is turning out to be nothing other than F force, which is purely magnetic in S frame. So basically electrostatics and relativity combined is leading to a magnetic force. Thank you.